Here is a strange fact to carry into the quiet of tonight. Your head is older than your feet. Not by much, by a few billionths of a second across a whole lifetime. But it is real, and it has been measured with two clocks, one set slightly above the other. The reason has nothing to do with biology and everything to do with the shape of the universe, with the way space and time are woven into a single fabric that bends around anything heavy. Tonight, slowly, we will take that fabric apart, thread by thread, until it stops feeling impossible. Before we begin, leave a comment and tell me which city and country you are listening from, and what the clock says where you are right now. I love picturing all these scattered lamps glowing at different hours. Now let your shoulders drop, and let us begin. So, let that be the last quick thing I say for a long while. From here, there is no hurry at all. We have the whole night, and the ideas we are going to walk through were built slowly over more than 300 years by people who often spent decades on a single question. There's no reason for us to move any faster than they did. If your eyes are already heavy, that is perfectly fine. You do not need to follow every word. You do not need to remember anything in the morning. The point of tonight is not to pass a test. The point is simply to let a few large and beautiful ideas drift through the room while you rest. The way you might leave a window cracked open so the sound of distant rain can come and go. Spacetime has a reputation. People hear the word and assume it belongs to geniuses and chalkboards, to equations that look like spilled alphabets. And it is true that the full mathematics is demanding. But the core of it, the part that actually matters, the part that changed how we understand reality, can be reached gently, with ordinary words and ordinary pictures. That is what we are going to do. We will start with things you already know in your body. Things like waiting and arriving, and being late, and standing in a room. And we will let those familiar feelings carry us, one careful step at a time, into something genuinely strange. By the end, the strangeness will still be there, but it will feel less like a wall and more like a wide, dark landscape you have learned to walk through in the dark. There is one promise I want to make you before we go any further, because I think it will help you relax. I am not going to ask you to be clever tonight. So many explanations of this subject seem designed to make you feel a little stupid, to remind you how hard the mathematics is and how few people truly grasp it. That is not what this is. Every single idea we touch tonight will be approached from something you already understand, something ordinary, a train, a clock, a falling cup, a kitchen table. We will never leap. We will only ever take one small step from where you already are. And if a step feels too big, that is my fault, not yours. And I will simply find a gentler one. You are allowed to drift in and out. You are allowed to lose the thread entirely and let my voice become nothing more than a soft current under the surface of your rest. The understanding, if it comes, will come on its own, the way understanding usually does, quietly, when you are not gripping it too tightly. It also helps to know that the people who built these ideas did not find them obvious either. They were not born understanding space-time. They were ordinary in their confusion, even when they were extraordinary in their patience. They argued with each other. They held wrong beliefs for years. They felt the same resistance in their own minds that you may feel in yours tonight. The same instinct that says this cannot possibly be right. The difference is only that they kept sitting with the discomfort long enough for it to soften into familiarity. We get to inherit the soft, familiar version, the one that has already been walked smooth by 100 years of careful thought. We are not pioneers tonight. We are walkers on a path that others cut through hard ground. and we can take it at whatever pace we like. Let us begin with the most ordinary thing in the world, which is the experience of being somewhere. Right now, think about where you are. You are in a particular place. Maybe a bedroom, maybe a sofa, maybe a narrow bed in a room that is not really yours. There are walls around you at certain distances. The ceiling is some number of feet above your head. The door is over there, the window is over here. All of that is space. It is the stage you are lying on. And you have a very confident sense of it. If someone asked you to point to the corner of the room, you could do it with your eyes closed. Space feels solid and given and obvious. It is just there, holding everything in place. Now think about when you are. It is some particular hour. The day has a name. There was a morning behind you, and there will be a morning ahead of you. And you are sliding forward through the hours whether you want to or not. That is time. And time feels completely different from space. Space you can walk around in. You can go left, then change your mind and go right, then come back to where you started. But time only goes one way. You cannot stroll back to this morning. You cannot revisit last Tuesday and stand in it again. Time feels like a river that only flows downstream, carrying you with it, never letting you turn around. So in everyday life, space and time feel like two separate things. One is a room you move through freely. The other is a current you are helplessly riding. They do not seem related at all. When you arrange to meet a friend, you actually give them two completely different kinds of instruction. You tell them where, which is space, the cafe on the corner, the third floor, the bench by the fountain. And you tell them when, which is time, 8 o'clock, after sunset, sometime tomorrow. Two instructions, two categories, where and when. For thousands of years, every human being who ever lived treated these as obviously, unquestionably separate. And here is the quiet mystery we are going to spend tonight unraveling. They are not separate, not really. Underneath the everyday appearance, where and when are two faces of one single thing. And that thing is what physicists call spacetime. The room you are lying in and the hour you are lying in it are not two different facts about your situation. They are two ways of measuring one combined fact. And the moment you accept that, a whole cascade of consequences follows. Time can stretch. Distances can shrink. Two events that look simultaneous to you can be clearly out of order to someone else, with neither of you wrong. And gravity, that thing that holds your blanket against you and keeps the floor under your feet, turns out not to be a force pulling at all, but a gentle slope in this very fabric. That is the journey. Let us take it slowly. To understand why anyone would ever combine space and time, we have to go back, and we have to start with a much simpler and much older puzzle. It is the puzzle of motion, of what it means to move, and whether there is any such thing as standing still. Picture a sailing ship, hundreds of years ago, gliding across a calm sea on a steady wind. Below the deck, in an enclosed cabin with no windows, a sailor is doing ordinary things. Pouring water from a jug into a cup, dropping a coin and watching it fall straight down, tossing an apple gently up and catching it. Here is the question that occupied some very serious minds. If that cabin is sealed and the sea is smooth, can the sailor tell that the ship is moving at all? And the surprising answer, worked out carefully 400 years ago, is no. He cannot. The water pours exactly the way it would pour if the ship were tied to the dock. The coin falls straight down, not slanting backward. The apple comes back to his hand. Everything inside the moving cabin behaves precisely as it would if nothing were moving at all. The man who thought most carefully about this was Galileo Galilei. Born in Pisa in 1564, in what is now Italy, Galileo is famous for many things: for his telescope, for his troubles with the church, for studying the moons of Jupiter. But one of his deepest contributions was almost invisible, because it was an idea about nothing happening. He realized that steady motion, smooth motion in a straight line at a constant speed, is undetectable from the inside. There is no experiment you can do in that sealed cabin to prove you are moving. And that means there is no such thing as being absolutely, truly at rest. The dock thinks it is standing still, and the ship is moving. But the ship could just as fairly say that it is standing still, and the dock, and the whole shoreline, and the entire earth are sliding past in the other direction. Both descriptions work. Neither is more correct than the other. We feel a small version of this all the time. You are sitting on a train in a station, and the train beside yours begins to creep forward. And for one disorienting second, you cannot tell whether your train is moving or theirs is. That little lurch of confusion in your stomach is Galileo's principle, alive in your own body. Motion, the steady kind, is only ever motion relative to something else. There is no cosmic answer to the question, am I really moving? There is only the question, am I moving relative to that? Now, hold on to that idea because it is going to matter enormously, and let us bring in the next great mind in the story. His name was Isaac Newton, born in England in 1643, the year after Galileo died, almost as if the universe were handing off a baton. Newton took Galileo's scattered insights and built them into a complete machine of physics, published in 1687 in a book whose short name is the Principia. Newton's laws of motion and his law of gravity were so powerful that they ran the science of the world for more than 200 years. They sent ships across oceans and eventually sent spacecraft to other planets. Newton was, by almost any measure, the most successful scientist who had ever lived. But Newton made one assumption that he never doubted, and that almost no one doubted for 2 centuries. And it is the assumption we are going to have to dismantle tonight. Newton believed that space was a fixed, eternal stage, the same for everyone, an absolute grid stretching out in all directions, whether anything was in it or not. And he believed that time was a single, universal clock, ticking at the same rate everywhere in the universe, the same for the sailor in the dock, the same on Earth, and the same on a distant star. One master clock that all of reality marched to, where, for Newton, was absolute. When, for Newton, was absolute. They were the great unmoving backdrop against which everything else happened. It is worth pausing here, because this is exactly how you and I instinctively feel about the world, even now. We feel that there is one true present moment, one universal now, shared by everyone, everywhere. We feel that a meter is a meter and a second is a second, no matter who is measuring. Newton simply wrote down what every human nervous system already believes. And for ordinary life, it works flawlessly. You can build a house, run a railway, fly a plane, all on Newton's absolute space and absolute time, and never notice a single thing wrong. The trouble came from an unexpected direction. It came from light. Through the 18th and 19th centuries, people were learning what light actually was. And in the 1860s, a Scottish physicist named James Clerk Maxwell, born in Edinburgh in 1831, achieved one of the great unifications in the history of science. He wrote down a set of equations that tied together electricity and magnetism, 2 things that had seemed separate, into a single phenomenon. And buried in those equations was a stunning surprise. They predicted waves, ripples of electric and magnetic fields traveling through space at a particular speed. And when Maxwell calculated that speed, It came out to roughly 300,000 kilometers per second, which was already known to be the speed of light. Light, it turned out, was an electromagnetic wave. The flickering of a candle and the invisible forces of a magnet were the same family of thing. This was a triumph, but it carried a thorn, and the thorn is where our whole story turns. Every wave that anyone had ever studied was a wave in something. Sound is a wave in air. Ocean waves are waves in water. Ripples run across the surface of a pond, but there has to be a pond. A wave, people reasoned, is a disturbance traveling through a medium, and you cannot have the disturbance without the stuff being disturbed. So if light was a wave, the obvious question was, a wave in what? What was the pond that light rippled across? What invisible substance filled all of space, even the vast emptiness between the stars, carrying the light of distant suns to our eyes? They gave this hypothetical substance a name. They called it the luminiferous ether, from old words meaning light-bearing. The ether was imagined as a perfectly transparent, perfectly thin, perfectly still material that filled the entire universe, the unmoving stage through which all light moved. And notice how neatly it fit with Newton. The ether could be the absolute space everyone had always assumed. It could be the thing that is truly at rest, the cosmic dock against which everything else, including the Earth, is moving. If you could only measure your motion through the ether, you would finally know your true, absolute speed through the universe. So people set out to measure it. And this is where two careful men, in a basement in Ohio, accidentally cracked the world open. The two men were Albert Michelson, born in 1852, and Edward Morley, born in 1838. In the year 1887, in Cleveland, Ohio, they performed what would become one of the most famous experiments in all of physics. And they did it by being extraordinarily, almost unreasonably, precise. Their reasoning was simple, even if their apparatus was not. If the Earth is flying through the still ether as it orbits the sun, then there should be a kind of wind, an ether wind, blowing past us. The same way you feel a wind on your face when you put your hand out of a moving car window, even on a calm day. And if there is an ether wind, then light traveling along the direction of that wind should move at a slightly different speed than light traveling across it. By comparing those two beams of light very carefully, they should be able to detect the wind, and finally measure the Earth's true motion through absolute space. They built an instrument of remarkable sensitivity. It floated on a pool of liquid mercury so that it could be turned smoothly in any direction. It split a single beam of light into two, sent them down two long arms set at right angles to each other, bounced them off mirrors, and brought them back together. If the two beams had traveled at even slightly different speeds, they would arrive slightly out of step, and that mismatch would show up as a faint, shifting pattern of light and dark bands. The experiment was so sensitive, it could detect differences far smaller than anyone needed. They turned it slowly through every angle, season after season, patiently, carefully, waiting for the pattern to shift. It never shifted. The light came back perfectly in step, every time, in every direction, in every season. There was no ether wind. There was, as far as their instrument could tell, no motion of the Earth through any ether at all. Now think about how strange this was. It was as if you stuck your hand out of a speeding car and felt no wind whatsoever. It made no sense. The Earth is unquestionably moving, racing around the sun at about 30 kilometers every second. If there were an ether, we should be plowing through it. But the light behaved as though we were sitting perfectly still. Michelson, who would later become the first American to win a Nobel Prize in the sciences, considered his beautiful experiment something close to a failure, because it had not found the thing it was built to find. He could not have known that finding nothing was, in fact, one of the most important discoveries ever made. The absence was the answer. The universe had quietly told us that something we deeply believed was simply wrong. For nearly 20 years, this hung in the air as a genuine crisis. Brilliant people tried to patch it. A pair of physicists, George Fitzgerald in Ireland and Hendrik Lorentz in the Netherlands, came up with a daring fix. What if objects moving through the ether actually shrank ever so slightly in the direction they were moving? If everything contracted by just the right amount, the experiment would come out null even though the ether was real. Lorentz, born in 1853, worked out the precise mathematics of this shrinking, equations that are still used and still bear his name. But it felt like a trick. A strange shrinking introduced only to hide the ether from us. And no one really understood why nature would behave that way. They had the right equations for the wrong reason. They were standing one step away from the truth and could not see it, because they refused to give up the one assumption that needed to go. And then, in 1905, a 26-year-old man who could not get a university job, who was working as a clerk in a patent office in Bern, Switzerland, examining other people's inventions for a modest salary, sat down and gave it up. His name was Albert Einstein. Let us slow down here, because this is the hinge of the entire night. Everything before this was the setup. Everything after it is the consequence. Einstein looked at the same puzzle everyone else was looking at, and he made a decision that was less about new mathematics and more about a kind of courage. He decided to take the experiments completely at face value. He decided to believe what nature was so plainly telling us, even though it sounded impossible. And then he asked calmly, what would the universe have to be like for this to be true? He started from two simple statements. The first was just Galileo's old principle, dusted off and trusted completely. The laws of physics are the same for everyone moving steadily. There is no special, privileged state of rest. The sailor in the cabin and the man on the dock are equally entitled to call themselves still. Nothing new there. That part felt safe. The second statement is the one that breaks the world. The speed of light is the same for every observer, no matter how they are moving. And I want you to sit with how outrageous that is, because everything in your ordinary experience screams that it cannot be right. Think about speeds the way you normally do. You are on a train moving at 100 kilometers an hour, and you walk forward down the aisle at 5 kilometers an hour. To someone standing on the platform, how fast are you moving? 105. Your speed and the train's speed simply add together. This is the most natural thing in the world. Throw a ball forward from a moving car, and it flies faster than if you threw it standing still, because the car's speed adds to your throw. Speeds add up. Everyone knows this. You know it in your bones. Now do the same thing with light. You are standing still and you shine a flashlight forward. The light races away from you at that famous speed, about 300,000 kilometers per second. Fine. Now you get on a spaceship and fly forward at, let us say, half the speed of light, and you shine the same flashlight forward. Common sense says the light should now be moving at 1.5 times the speed of light, your speed plus the light's speed, just like you walking on the train. But that is not what happens. The light moves away from you at exactly the same speed as before, not faster. Exactly the speed of light. And here is the part that truly hurts. Someone watching you fly past, standing still on a planet, also measures that same light beam moving at exactly the speed of light relative to them. Not the speed of light plus your spaceship's speed, just the speed of light. Both of you, moving very differently, measure the very same beam at the very same speed. This is where people's eyes start to glaze over, and that is completely understandable, because it sounds like a contradiction. So let me not rush past it. Let me give you the way to make peace with it. The key is to remember what speed actually is. Speed is a distance divided by a time. Kilometers per hour, meters per second. It is always a measurement of how much space you cover in how much time. So if two people who are moving differently both measure light at the exact same speed, and speed is space divided by time, then something has to give. Either they are not measuring space the same way, or they are not measuring time the same way. And the answer that took the courage of that young clerk in Bern to accept, is that they are not measuring either one the same way. The speed of light stays fixed, locked, unchangeable. And to keep it fixed, space itself and time itself have to bend and stretch around it. Read that again slowly, because it is the whole secret. We always assumed that space and time were the rigid, fixed things, and that speeds were flexible, adding and subtracting freely. Einstein turned it inside out. The speed of light is the rigid, fixed thing, and space and time are the flexible ones. Time is not a universal clock ticking the same for everyone. Space is not an absolute grid measured the same by everyone. They flex. They have to, in order to protect that one unchanging speed. So what does this flexing actually look like? Let me build it up gently with a picture you can hold in your mind. Imagine the simplest possible clock. It is not a clock with hands or numbers. It is just a single pulse of light bouncing straight up and down between two mirrors, one on the floor and one on the ceiling of a small box. Up, bounce, up, bounce, down. Each round trip of the light is one tick. Because light always moves at the same fixed speed, this is a perfect, reliable clock. The light has a certain distance to travel, up to the mirror and back, and at a fixed speed that takes a fixed amount of time. Tick, tick, tick. Now you are holding this light clock and you are standing still, watching it tick steadily. Easy. The light goes straight up and straight down, a simple vertical line, and you count the ticks. Now I take the same clock and I put it on a train that goes rushing past you very, very fast. You are still standing on the platform, watching the clock as it flies by. And here's the thing you have to picture carefully. From your point of view on the platform, the light inside that moving clock is not just going up and down anymore. Because the whole clock is moving sideways while the light is traveling. The light has to move diagonally to catch up to the mirror, which has shifted sideways since the pulse left. Up and over, then down and over. The light, as you see it, traces out a long zigzag, like the path of a ball bouncing while you carry it across a room. Now look at those two paths side by side. The straight up and down path is short. The diagonal zigzag path is longer because a slanted line covering both upward and sideways distance is always longer than a straight vertical line. The light has farther to travel in the moving clock, as you see it. But, and this is the iron rule that cannot be broken, the light cannot speed up to cover that longer path more quickly. Light always moves at exactly the same speed for everyone. So if the light has a longer path to cover and it cannot go any faster, then each tick of that moving clock must take longer. The moving clock, as seen by you on the platform, ticks more slowly than your own clock. Time itself, on that train, is running slow. This is called time dilation, And it is not an illusion or a trick of perception. It is real. A clock that moves relative to you genuinely runs slow compared to your clock. And it gets stranger in a way that is beautifully symmetric. Because all steady motion is relative, remember Galileo. The person on the train has every right to say that they are the one standing still and you are the one rushing past. And from their point of view, your clock is the one ticking slowly. Each of you sees the other's time running slow. Neither of you is wrong. There is no universal clock to settle the argument because there is no universal clock at all. That was the very thing we had to give up. I know how this sits in the stomach. It feels like it should lead to a paradox, like the two stories cannot both be true. And there is a famous puzzle, the twin paradox, that pushes exactly on this. But the resolution, which we will not chase fully tonight, is that the symmetry only holds for steady, unchanging motion. The moment one twin turns around to come home, they have to accelerate, they have to change their motion, and that breaks the perfect symmetry. And that is the twin who comes back younger. It is not a contradiction. It is just a universe more subtle than our instincts. And it is not only time that flexes. Space flexes too. Remember that strange shrinking that Lorentz invented to hide the ether? It was real after all, just not for the reason he thought. An object moving very fast relative to you is genuinely shortened in the direction of its motion as you measure it. A spaceship streaking past you would be measured by you as a little squashed, a little compressed front to back, even while the people inside it feel perfectly normal-sized and measure you as the squashed one. Space contracts. Time dilates. The two of them bend together in just the precise amounts needed to keep the speed of light the same for everyone. Nature is not being cruel or arbitrary. It is being consistent. It is protecting one law at the cost of all our comfortable assumptions. Let us pause and breathe here, because we have just walked through the heart of what is called special relativity, the theory Einstein published in that single remarkable year of 1905, a year in which, almost unbelievably, he also published the work that explained the photoelectric effect, the work that proved atoms were real, and the short note that contained the most famous equation in the world, the one relating energy and mass. He did all of that while approving patents for a living. He was not yet a professor, he was barely known, and he had just quietly overturned 2 centuries of certainty about the nature of reality. But there is one more consequence of special relativity, and it is the one that finally forces space and time to fuse into a single thing. It is the strangest of all, and it is the one that, once you feel it, never quite leaves you. It is about the word now. Here is the question. When you say that 2 things are happening at the same time in 2 different places, what do you actually mean? Suppose a lamp turns on in your room, and at the same instant, a lamp turns on in a room across the city. Same time, different places. Simultaneous. It seems like an absolutely clear and simple statement. Either 2 things happen at once, or they do not. Surely that is just a fact. True for everyone. It is not. And this is perhaps the single most disorienting result in all of physics. More than time dilation, more than length contraction. Whether 2 distant events happen at the same time depends on who is asking. 2 events that are perfectly simultaneous for you can be clearly one after the other for someone moving past you. And again, neither of you is mistaken. There is no true, universal answer to the question of what is happening right now far away from you. The cosmic now, the single shared present moment that Newton believed in and that you feel in your bones, does not exist. Let me give you the picture Einstein himself liked to use, slowed down and softened for the hour. Imagine a long train moving smoothly along a track, and imagine you are standing on the embankment beside the track, watching it pass. Now imagine that two bolts of lightning strike the ground, one at the very front of the train and one at the very back, at the exact same moment as far as you are concerned. You are standing precisely halfway between the two strike points, and the flashes of light from each one reach your eyes at the same instant. Since you are in the middle, and light travels at the same speed both ways, you conclude, quite correctly for you, that the two strikes happened simultaneously. Now think about a passenger sitting in the exact center of the train, moving forward with it. At the moment the lightning strikes, this passenger happens to be right next to you, but they are gliding forward toward the front strike and away from the back strike. The light from both strikes is traveling toward this passenger at, you guessed it, the same fixed speed. But the passenger is moving toward the place where the front bolt struck and away from where the back bolt struck. So the light from the front reaches them a little sooner, and the light from the back reaches them a little later. From inside the train, the front strike clearly happened first, and the back strike happened afterward. Not at the same time. One, then the other. So who is right? You on the embankment saw them happen together. The passenger on the train saw the front one happen first. And the answer that should make the back of your neck tingle a little, is that you are both completely right. There is no further fact of the matter. Simultaneity, the question of whether two distant things happen at the same time, is not absolute. It depends on your motion. Change how you are moving, and you literally change which distant events count as happening now. This is the moment, historically and conceptually, when space and time can no longer be kept apart. Because look at what just happened. By moving through space, the passenger changed what was happening in time, far away, in two different places. Their motion through space reshuffled the order of events in time. Space and time are not behaving like two separate things anymore. They are bleeding into each other. A change in one is a change in the other. They are reacting together, like two ingredients that have already been stirred into the same batter and can no longer be picked apart. And here is where a quiet, less famous figure steps into the story and gives it its true shape. His name was Hermann Minkowski, born in 1864, a brilliant mathematician who, years earlier in Zurich, had actually been one of Einstein's teachers. He had not been especially impressed by the young Einstein as a student, once describing him more or less as a lazy dog. But when his former pupil's strange new theory landed in the world, Minkowski saw something in it that Einstein himself had not yet fully drawn out. He saw the geometry hiding underneath. In 1908, in a lecture in the German city of Cologne, Minkowski stood up and announced, in effect, that from then on, space alone and time alone were destined to fade into mere shadows, and that only a union of the two would hold any independent reality. It was a bold thing to say out loud. What he meant was this: stop thinking of space as a three-dimensional stage that the universe sits in, and time as a separate river flowing alongside it. Start thinking of them as a single four-dimensional thing. 3 dimensions of space woven together with 1 dimension of time, all stitched into one continuous fabric. He gave it a name that we still use. He called it the world. We call it Spacetime. Let me make this picture as gentle and as concrete as I can, because the word four-dimensional tends to frighten people, and it really should not. You do not need to imagine some bizarre extra direction poking out of the room. You already live in space-time, naturally, every moment of your life. You just describe it in two halves out of habit. Think back to meeting your friend at the cafe. You gave them a where, the corner of two streets, which is really three numbers if you want to be precise. How far east, how far north, how high up, the third floor. Three numbers for space. And then you gave them a when, 8 o'clock, which is one more number, a position in time. Put those together and you have four numbers that pin down one single point, one specific event, the moment and place where you and your friend actually meet. Three numbers of space, one number of time, four numbers for one event. That is a point in space-time. Every event that has ever happened or ever will happen is a single point in this four-dimensional fabric, located by where and when together. Your birth is a point in space-time. This very moment, you lying here listening, is a point in space-time. They are all stitched into the same cloth. Now here is the analogy I want to give you to hold. The one I think makes the whole strange business of simultaneity finally feel imaginable. I want you to picture a loaf of bread. Picture a long, whole, unsliced loaf lying on a kitchen table. Let the length of the loaf, running away from you, be time, the past at one end and the future at the other. And let each thin slice you could cut across the loaf be a single moment, a now, a snapshot of all of space at one instant. When you take a knife and cut the loaf straight across, perpendicular to the table, you get one clean slice, and everything in that slice is, by your reckoning, happening at the same time. That slice is your present moment, your now, spread across all of space. Here is the thing that special relativity tells us, and it is so simple once you see the loaf. Different observers slice the loaf at different angles. Someone moving relative to you does not cut the loaf straight across the way you do. They cut it at a slight tilt. And because their slice is tilted, it scoops up slightly different events as belonging to the same moment. A point that lands on your straight slice, your now, might land a little ahead or a little behind on their tilted slice. That is the whole mystery of simultaneity, made visible. There is one loaf, one single four-dimensional reality, the same for everyone. But there is no single correct way to slice it into nows. The loaf is real and shared. The slicing is personal. Your present and my present are different cuts through the same bread. I find that picture deeply calming somehow. All of space-time, every event, already laid out as one whole loaf. The past not gone, the future not absent, just other parts of the same fabric, with the present being only the particular slice each of us happens to be cutting as we move along. There is something restful in it. The idea that reality is whole and entire, and that our sense of a rushing, vanishing present is just the angle of our own small knife. But if everyone slices the loaf differently, if there is no shared now, you might start to worry about something. You might worry that everything falls into chaos, that cause and effect break down, that maybe someone could see an effect happen before its cause, see the glass shatter before it was dropped. And this is a real and serious worry, and the universe has a beautiful answer to it. And the answer is the shape called the light cone. Let me build it for you slowly, because it is one of the loveliest ideas in all of this. Go back to a single event, a single point in space-time. Let it be, say, a candle being lit, right here, right now. From that one event, light begins to spread outward in every direction at its fixed speed. After 1 second, that light has reached everything within 300,000 kilometers. After 2 seconds, twice as far. The light forms an expanding sphere. growing outward through space as time moves forward. Now, if we draw this, with time running upward and space running sideways, that expanding sphere of light traces out the shape of a cone, opening upward into the future. Everything inside that upward cone is a place and time that the light from your candle could possibly reach. Everything inside it is part of the candle's possible future, the set of all events the candle could influence. And there is a matching cone opening downward, into the past. That lower cone contains every event whose light could have reached your candle by now, every place and time that could possibly have influenced this moment. The two cones meet at a single point, the here and now of the candle, like two ice cream cones touching tip to tip. Now here is the deep thing, the thing that saves cause and effect. Nothing, no object, no signal, no influence of any kind, can travel faster than light. The speed of light is not just the speed of light. It is the speed limit of the universe, the maximum rate at which any cause can reach out and produce any effect. Which means the candle can only ever influence events inside its future cone, the upward one. And the candle can only ever have been influenced by events inside its past cone, the downward one. Cause and effect live entirely inside the cones. And what about everything outside the cones, off to the sides? There is a whole region of space-time, an enormous region, that is neither in your future cone nor your past cone. These are events so far away in space and so close in time that not even light could get from them to you or from you to them in time to matter. Physicists give this region a wonderful, lonely name. They call it the elsewhere. Events in your elsewhere cannot affect you and you cannot affect them. They are causally cut off. And here is the resolution to that worry about chaos. The order of events inside your light cones, the order of any two events that could possibly influence each other, is the same for everyone, no matter how they are moving. Every observer agrees that the cause came before the effect. The only events whose order can get reshuffled, the only ones where you might disagree about which happened first, are events in each other's elsewhere, events that could never have influenced one another anyway. So nothing important ever gets scrambled. The universe protects cause and effect with exquisite care. You can disagree about the timing of things that could never touch. You can never disagree about the order of things that could. I want to give you one more gift from special relativity before we let gravity into the story, because it is the thing that finally puts solid ground back under your feet after all this shifting and slicing. You might feel, by now, that nothing is fixed, that everyone measures different times and different lengths and different nows, that there is no agreement on anything at all. But that is not quite true. There is something everyone agrees on. There is one quantity that comes out exactly the same for every observer, no matter their motion. And it is the deepest measurement in all of space-time. It is called the space-time interval. Here is the idea, kept simple. Take any two events. Two people will disagree about the distance in space between them, because space contracts. Two people will disagree about the time between them, because time dilates. But if you combine the space separation and the time separation in a particular way, a specific blend of the two, that combined number, the space-time interval, comes out identical for everyone. It is the true, observer-independent distance between two events in the fabric, the real separation in the loaf itself, before anyone slices it. The space part and the time part each shift around from person to person, but they shift in a coordinated dance, one growing exactly as much as the other shrinks, so that the blended interval stays locked. This is what Minkowski really gave us. Not just the idea that space and time are one fabric, but the precise geometry of that fabric, the rule for measuring real distances in it. Spacetime is not lawless. It simply obeys a deeper law than the ones we grew up with. There is one more way to picture all of this that I find quietly beautiful, and I will offer it gently because it is more of a poem than a proof. You can think of everything in the universe as always moving through space-time at one single speed, the speed of light. Not through space, through space-time, the combined thing. When you are sitting perfectly still in space, all of your motion is pointed in the time direction. You are racing into the future at full speed, which is why, for you, time passes at its normal brisk rate. But when you start moving through space, you have to borrow some of that motion and aim it sideways, into the space directions. And since your total speed through space-time is fixed, every bit of motion you spend on moving through space is motion you can no longer spend moving through time. So your progress through time slows down. That is time dilation, seen from a higher window. A thing at rest spends all its speed on time. Light itself spends all its speed on space, which is exactly why, for a beam of light, no time passes at all. And you and I, moving slowly through our small lives, spend almost all of our speed traveling into tomorrow, with only the tiniest sliver aimed sideways. We are, all of us, mostly time travelers, drifting forward at nearly the full speed of light through the only direction we cannot steer. Before we leave the world of steady motion and let gravity into the room, I want to spend a little while on two questions that almost everyone asks at this point. Because answering them gently will make everything that came before feel more solid, less like a clever trick and more like simple truth. The first question is, why light? Why should the speed of light, of all things, be the unbreakable speed limit of the universe, the rigid thing around which space and time have to bend? And the second question is, can we actually be sure any of this is real? Or is it just a story that happens to fit some equations? Let us take the first one slowly. The phrase "the speed of light" is a little misleading, and it has confused people for 100 years. The speed we keep talking about is not really about light at all. It is a fundamental feature of space-time itself, a kind of maximum rate at which any cause can produce any effect, anywhere, ever. Light just happens to travel at that maximum speed, because light has no mass, and anything with no mass is required to move at exactly that limit, no faster and no slower. If light had never existed, the speed limit would still be there, woven into the fabric. We could just as accurately call it the speed of causality. The fastest that anything, a push, a signal, a piece of news, a consequence, can move from one event to another. Light is simply the most familiar thing that runs at full speed. Now, why can nothing with mass ever reach that speed? Here is the gentle way to feel it. When you push on an object to speed it up, you are giving it energy, and that energy goes into its motion. But Einstein discovered in that same miraculous year that energy and mass are two forms of the same thing, captured in the most famous equation ever written, which says that the energy locked inside an object equals its mass multiplied by the speed of light squared. Because that speed is such an enormous number, and it is squared on top of that, even a tiny amount of mass holds a staggering amount of energy. This is the secret behind the sun, which shines by converting a small fraction of its mass into light. And it is the secret behind the gravitational waves we will return to later. But the equation runs both ways. Just as mass can become energy, energy adds to mass. And so, as you pour energy into an object to make it go faster, some of that energy turns into extra mass. making the object heavier, making it harder to speed up further. The faster it goes, the heavier it gets, the more energy the next bit of speed demands. As you approach the speed of light, the object becomes effectively more and more massive, and it would take an infinite amount of energy to push it the final step to the limit itself. The universe does not forbid faster than light travel with a sign on a wall. It simply makes the cost climb to infinity, so the door quietly closes on its own. That is the answer to the first question, as softly as I can put it. The speed limit is built into the geometry of space-time. Light rides it because it is massless, and the rest of us can never quite reach it because reaching it would cost everything there is. The second question is the one I love most, because the answer is so concrete, you can almost hold it. Is any of this real? And the universe gives us a wonderful, humble little proof, raining down on your roof at this very moment. High up in the atmosphere, dozens of kilometers above you, cosmic rays from deep space are constantly slamming into the upper air. And when they do, they create tiny particles called muons. A muon is a heavier cousin of the electron, and it is profoundly unstable. Left to itself, a muon survives for only about 2/millionths of a second before it falls apart. Now, 2/millionths of a second is not much time, and even moving at nearly the speed of light, a muon should only be able to travel a few hundred meters before it dies. By that arithmetic, almost none of them should ever reach the ground. They are born far too high up. They should all decay in the air, long before they get anywhere near you. And yet, they reach the ground in enormous numbers. They are passing through you, harmlessly, several of them through your body every second, as you lie there. Detectors at sea level catch them constantly. How? The answer is the very time dilation we walked through with the light clock. The muons are moving so fast that from our point of view on the ground, their internal clocks run slow. Their 2/millionths of a second stretches out, from our vantage, into enough time to complete the long fall to the surface. And from the muon's own point of view, where its short life is perfectly normal, it is the distance that has changed. The height of the atmosphere contracted down, by the length contraction we also met, into a thin enough layer that it can cross it before dying. Two different descriptions, the dilated time and the contracted distance, and both of them deliver the muon safely to the ground, exactly as observed. These particles are not a thought experiment. They are real, they are falling through your room right now, and they only survive the trip because space and time genuinely bend the way Einstein said. The proof is quite literally over your head. And now, let me return, just briefly, to that twin puzzle I mentioned earlier and set aside, because it deserves a slightly fuller rest. Imagine two siblings, the same age. One stays home on Earth, the other climbs into a fast rocket, flies out toward a distant star at close to the speed of light, then turns around and comes home. When the traveler returns, they are genuinely younger than the sibling who stayed. Not in appearance only, but in every way that counts. Fewer heartbeats have passed for them, fewer breaths, fewer years. They have, in a real sense, traveled into their sibling's future. People find this maddening because they say, motion is relative. So why is it not symmetric? Why does the traveler age less rather than the stay at home? Could you not just as well say the Earth flew away and came back? The quiet resolution is this. The two journeys are not the same kind of journey. The sibling who stayed home moved smoothly through space-time the whole time, a single straight path. But the traveler had to fire engines to launch, fire them again to turn around at the distant star, and fire them once more to slow down and land. The traveler felt those changes in motion, pressed into the seat, while the stay-at-home felt nothing of the sort. Their two paths through the four-dimensional fabric were genuinely different shapes, and in space-time, strange as it sounds, the longer-looking, bent, out-and-back path is actually the one along which less time passes. The straight path home accumulates the most time. So the traveler, taking the bent road, returns younger, with no contradiction at all. It is not that one of them was really moving and the other really still. It is that they took two different routes through the same fabric, and the fabric measured each route honestly. Time is not a universal river after all. It is a distance, a length of your own particular path through space-time, and different paths can have different lengths, just as two roads between the same two towns can be longer or shorter. Let us rest there for a moment. We have built a great deal tonight, and we have only used special relativity, the theory of steady motion, of trains and spaceships gliding along without speeding up or slowing down or turning. Everything so far has happened in a universe with no gravity, an empty universe of straight, smooth, unchanging motion. And that empty universe already gave us a single four-dimensional fabric with flexible time, flexible space, tilted slices of now, protective light cones, and one true invariant interval underneath it all. But we do not live in an empty universe. We live in a universe full of heavy things, planets, stars, the bed beneath you, your own body. And the moment Einstein asked what happens to his beautiful flat fabric when you fill it with mass, the story took its final, deepest turn. It took him another 10 years to work it out. It nearly broke him. And when it was done, it explained the oldest mystery of all, the one we have all felt every single day of our lives and never thought to question. It explained why things fall. The turning point came to Einstein in 1907, 2 years after his miracle year, while he was still sitting at his desk in the patent office. He later called it the happiest thought of his life, which is a touching thing for a person to say about an idea. The thought was simple, almost childlike, and like the best ideas, it was about noticing something obvious that no one else had bothered to notice. He realized that a person falling freely does not feel their own weight. Sit with that. If you were to step off a high ledge in the moment of falling, before anything stops you, you would feel weightless. Your stomach lifts. Everything in your pockets falls exactly alongside you. If you let go of a set of keys mid-fall, they would not drop away from you, because they are falling at the very same rate you are. They would simply hang there beside you, as if floating. We have all seen this. It is exactly what astronauts experience on the space station, drifting weightlessly. People often imagine that astronauts float because there is no gravity up there. But that is not true at all. Gravity is still strong where they orbit, nearly as strong as on the ground. They float because they are falling endlessly around the Earth. And a person in free fall feels no gravity, just as Einstein realized in 1907. Now turn the thought around, which is where it gets powerful. Imagine you wake up in a sealed room with no windows, and you feel your normal weight pressing your back into the bed, your feet wanting to find the floor. There are two completely different explanations for that feeling, and here is the astonishing part. There is no experiment you could do inside the room to tell them apart. One explanation is that your room is sitting still on the surface of a planet, and the planet's gravity is pulling you down. The other explanation is that your room is far out in empty space, with no planet anywhere near, and the whole room is being dragged upward, accelerating, like the floor of an elevator shooting up, pressing against you. Standing on a planet and accelerating through empty space feel exactly, precisely, identically the same. This is called the equivalence principle, and it is the seed from which all of gravity, properly understood, grows. Because look at what it implies. We already learned from special relativity that acceleration and motion bend the path of light and warp the measurements of space and time. And now we are being told that the feeling of gravity is exactly the same as the feeling of acceleration. So gravity too must bend the path of light. Gravity too must warp space and time. Gravity is not some separate force layered on top of the fabric. Gravity is the fabric, bending. Here is the new picture, the one Einstein spent 10 hard years building into precise mathematics. With crucial help from old friends and from the geometry that Minkowski and others had developed. A massive object, a star, a planet, your own body, does not reach out and pull on things with an invisible rope. Instead, it bends the space-time around it. It curves the fabric. And other objects, moving through that curved fabric, simply follow the straightest possible path they can find through the curves. What looks to us like a pull, like a force dragging things down, is really just objects coasting along the natural grooves that mass has carved into space-time. The moon is not held to the Earth by a tether. The Earth has made a great gentle valley in the fabric of space-time around it, and the moon is rolling along the rim of that valley, going as straight as it possibly can, which, in curved space-time, means going in a circle. A planet orbiting the sun is doing nothing more strenuous than a marble rolling around the inside of a curved bowl, following the shape it has been given. And the reason your blanket presses down on you tonight, the reason the floor holds your feet, the reason a dropped cup falls toward the ground, is that the Earth has bent the space-time in this room. And everything, including you, is trying to follow the straightest path through that bend, which points, here, downward, toward the center of the Earth. Let me anticipate the question that always comes up here, because it is a good one, and it confused people for years. If everything is just following the straightest path, why do things fall when they are sitting still? You are not moving through space at all when you drop a cup. So why does it move? And the answer is the most beautiful single sentence in this whole night. You are never sitting still. Remember, you are always moving through space-time, always racing forward through time even when you are perfectly still in space. And near a massive object, time itself is part of what gets curved. The cup, just by moving forward through time, the way everything must, gets gently steered by the curvature toward the Earth. It falls through space because it cannot help moving through time. And here, time and space are bent together. Gravity is the curvature of time even more than the curvature of space. That faint warping of time near the ground. That is what reaches up and pulls. And now you can finally understand the strange fact I opened with. The one about your head being older than your feet. Near a massive body like the Earth, time runs very slightly slower the closer you are to it, because the curvature is stronger there. Your feet, being closer to the ground, sit in slightly more sharply curved space-time, where time crawls just a hair more slowly. Your head, higher up, sits where the curve is gentler and time runs just a hair faster. Over a lifetime, your head accumulates a few extra billionths of a second compared to your feet. It is unmeasurably small to you, but it is not zero, and it has been measured in laboratories with clocks accurate enough to detect the difference across the height of a single staircase. The shape of space-time is not a metaphor. It is something you can put on a table and read off a dial. I want to linger for a little while on those 10 years between the happy thought and the finished theory, because the smooth way I have told it hides an enormous amount of struggle. And there is something comforting, late at night, and remembering that even the greatest minds spend years lost and confused before anything becomes clear. Einstein had his beautiful insight in 1907 that gravity and acceleration are the same, and he could see dimly that this meant space-time had to curve. But seeing that it must curve and knowing how to describe a curved, four-dimensional fabric in precise mathematics are two completely different things. And Einstein, for all his genius, did not have that mathematics. He had been, in his student days, somewhat dismissive of the more abstract corners of geometry. Now he needed exactly those corners, and he did not know his way around them. So he did what wise people do. He asked an old friend for help. The friend was Marcel Grossmann, a former classmate from his Zurich student days, a gifted mathematician who had, years earlier, lent Einstein his careful lecture notes when the young Einstein had been skipping class. Now Einstein went to him again and said, "More or less, you must help me, or I will go mad." Grossmann pointed him toward a branch of mathematics that had been developed decades before, for reasons that had nothing to do with physics at all. It was the geometry of curved surfaces and curved spaces, worked out in the 1800s by mathematicians like Carl Friedrich Gauss, who had studied the curvature of ordinary surfaces, and his student Bernhard Riemann, who had taken the idea and boldly extended it to spaces of any number of dimensions, including ones no one could picture. Riemann had built, purely out of curiosity, the exact mathematical language needed to describe a bending four-dimensional fabric, and he had done it half a century before anyone knew the universe would need it. It is one of the quiet miracles of science. How often the tool is sitting on the shelf, finished and waiting, years before the problem arrives. Even with the right mathematics in hand, the work was brutal. Einstein wrestled with the equations for years, taking wrong turns, convincing himself he had the answer, and then discovering it could not be right, throwing out months of work and starting again. He grew exhausted and unwell. And then, in the autumn of 1915, it came down to a kind of race. A brilliant mathematician named David Hilbert, in the German city of Göttingen, had grasped what Einstein was attempting and was closing in on the same equations from the mathematical side. For a few tense weeks in November of 1915, the two of them were circling the same goal almost simultaneously. Einstein, working at a feverish pace, presenting new results week after week to the Academy in Berlin, reached the final, correct field equations and presented them in late November. The equations are compact enough to write on a single line, and yet they contain, folded inside, the orbits of the planets, the bending of starlight, the slowing of clocks near mass, the existence of black holes, the ripples of gravitational waves, and the expansion of the entire universe. One short line of mathematics describing how matter tells space-time how to curve, and how curved space-time tells matter how to move. It had taken him 8 years of his life. He was 36 years old, and he had just written, arguably, the most beautiful idea any single human being has ever had. When Einstein finished this theory, which he called general relativity and presented in its complete form in late 1915, it was an extraordinary intellectual achievement. But it was also, at first, just a claim. A beautiful claim, an elegant claim. But the universe does not care about elegance. It needed to be tested. And the theory made one prediction sharp enough to check. If massive objects bend space-time, then they should bend the path of light passing nearby. Light from a distant star, grazing past the edge of the sun on its way to Earth, should be deflected by a tiny, specific amount, twice as much as Newton's old theory would have allowed. The trouble was, you can never see stars near the sun, because the sun's glare drowns them out. except during a total solar eclipse, when the moon blocks the sun and the sky goes dark in the middle of the day, and the stars near the sun's edge become briefly visible. So in 1919, just after the end of the First World War, an English astronomer named Arthur Eddington, born in 1882, organized expeditions to do exactly this. A total eclipse was due in May of that year, and to see it well, you had to be near the equator. Eddington himself traveled to the small island of Principe, off the west coast of Africa, while a second team went to the town of Sobral in northern Brazil. The plan was to photograph the stars near the darkened sun during the eclipse, then compare their positions to where those same stars sat in the night sky months later, when the sun was nowhere near them. If Einstein was right, the stars near the sun would appear very slightly shifted out of place, because their light had been bent as it skimmed past the sun's gravity. On the day of the eclipse at Principe, it was cloudy, and Eddington must have felt the whole effort slipping away. But the clouds broke just enough near the moment of totality, and he got his photographs. The measurements were painstaking, the shifts almost impossibly small, fractions of a hair's breadth on a photographic plate. But when the analysis was done and announced to the world in November of 1919, the verdict was clear. The starlight had been bent, and it had been bent by close to the amount Einstein predicted, not the smaller amount of Newton. The news ran in newspapers around the world. A relatively obscure physicist became, almost overnight, the most famous scientist alive. Newton's 200-year reign as the final word on gravity was over, gently set aside. Not because he had been foolish, but because the universe was deeper than his beautiful theory could reach. Gravity was not a force. Gravity was the shape of space-time, and starlight had traced that shape across the dark for everyone to see. That same bending of light, the very effect Eddington measured during those few stolen minutes of darkness, has since turned from a curiosity into one of the most powerful tools astronomers possess. And I want to share it with you, because it is quietly miraculous. If a massive object bends the light passing near it, then a truly enormous mass, like an entire cluster of galaxies, can act like a giant, clumsy lens floating in space. Light from some far more distant galaxy, traveling toward us, passes near the heavy cluster and gets bent around it, the way light bends through the curved glass of a magnifying lens or the foot of a wine glass. And so we can see, behind the cluster, the image of a galaxy that would otherwise be far too faint and far too distant to detect at all, its light gathered and focused and brightened by the curved space-time in between. Sometimes the alignment is so perfect that the distant galaxy's light is smeared all the way around the cluster into a glowing circle, a phenomenon called an Einstein ring, a halo of ancient light bent into a near-perfect loop by the warping of the fabric. We use these natural lenses now as telescopes built by gravity itself, peering at galaxies near the dawn of time that no human-made instrument could otherwise reach. And there is a deeper gift hidden in the lensing. By measuring exactly how much the light is bent, we can weigh the thing doing the bending, because the amount of curvature tells us how much mass is present. And when astronomers do this, they find something unsettling and wonderful. The galaxies are bending light far more strongly than the matter we can see could ever account for. There must be a great deal of mass out there that gives off no light at all, invisible, silent, betrayed only by the way it curves space-time and bends the starlight passing through. We call it dark matter, and we do not yet know what it is. But we know it is there, and we know it because of the very same principle a young clerk dreamed up at his desk, and a determined astronomer photographed through a break in the clouds. The bending of light has become a way of feeling in the dark, for things we cannot see. There is a quieter figure I want to name here too, because his story always moves me. While Einstein was still polishing his theory, a German physicist named Karl Schwarzschild, born in 1873, was serving as a soldier on the Russian front during the war, calculating artillery trajectories in the cold. In the middle of that misery, he read Einstein's new equations and, astonishingly, found the first exact solution to them, a precise mathematical description of the curved spacetime around a single round map. Hidden inside his solution was the first real hint of what we now call black holes, regions where mass bends spacetime so steeply that nothing, not even light, can climb back out. Schwarzschild sent his work to Einstein, who was amazed that anyone had solved the equation so quickly, let alone from a battlefield. Schwarzschild fell ill at the front and died in 1916, only months later, at the age of 42. He never knew how central his battlefield calculation would become. His name now sits permanently on the very edge of every black hole in the universe, the boundary of no return, the Schwarzschild radius. The eclipse of 1919 was only the beginning of the confirmations, and over the following decades, the evidence kept arriving, each piece smaller and more precise than the last, until doubting general relativity became almost impossible. Let me give you two of my favorites, because they are wonderfully down to earth, far more modest than colliding black holes, and yet they show the bending of time happening right here on our own small planet. In 1959, two physicists at Harvard University, Robert Pound and his student Glenn Rebka, set out to measure whether time really does run slower, lower down, closer to the Earth, exactly as the curvature of space-time predicts. The difference over the height of a building is staggeringly tiny, far too small to see with any clock. So they did something ingenious. Instead of clocks, they used light itself as the timekeeper, sending a beam of very precise radiation up a tower about 22 meters tall in the physics building. If time ran slightly faster at the top, the light should arrive very slightly shifted in its frequency, a change of just a few parts in 1,000 trillion. It sounds impossible to detect. But they detected it, and it matched Einstein's prediction. Over the height of a single staircase, they had caught time flowing at two different rates. The fabric was bending, measurably, in an ordinary building in Massachusetts. Then, in 1971, came an experiment so charmingly simple that it almost sounds like a joke. Two scientists, Joseph Haefele and Richard Keating, took 4 extremely precise atomic clocks, bought ordinary plane tickets, and flew the clocks around the world on commercial airliners, first eastward, then westward, while keeping identical clocks still on the ground for comparison. By Einstein's theories, the flying clocks should disagree with the ground clocks by a tiny amount, because of two effects pulling in opposite directions. The speed of the planes would make the flying clocks run a little slow. By special relativity, the same effect as the light clock on the train. But the altitude of the planes, higher up where space-time is less curved, would make them run a little fast by general relativity, the same reason your head ages faster than your feet. The two effects would partly cancel, leaving a net difference of mere billionths of a second. When the planes landed and the clocks were compared, the differences were there in just the predicted amounts. People had carried time dilation around the world in the overhead luggage and brought back the proof in a metal box. After that, there was very little room left for doubt. The strange theory of the patent clerk was simply how the universe works. Let us take a slow breath and feel the whole shape of what we have built. Because I think the pieces are ready to settle into place now, the way they do when you have been turning a difficult idea over for a long while. and it suddenly holds still. We began with the plain feeling that space and time are separate. Space, a room you move through. Time, a river that carries you. Two different things, where and when. And then, following light, following the stubborn fact that its speed is the same for everyone, we were forced to bend both of them, to let time stretch and space contract, to give up the single universal now, to slice the loaf at our own angles. And in giving all that up, we found something better underneath, a single four-dimensional fabric, space-time, real and whole and shared, with a true geometry of its own, a true distance between events that everyone can agree on, even when they cannot agree on space alone or time alone. And then we filled that fabric with mass, and watched it curve, and discovered that the oldest force we know, gravity, the homely pull that holds us in our beds, is nothing but the curving of that fabric, things falling because they are following the straightest path through a bent and gently sloping reality. That is the answer to the mystery we set out with. Why are space and time one thing? Because the speed of light demands it, and because gravity is built out of it. They are not two things that happen to be related. They are one thing, seen from two habits of thought. And once you hold them as one, the universe stops being a stage with actors and a clock on the wall, and becomes something far stranger and far more graceful. A single bending fabric with everything that exists riding along its curves and its slopes, including you, lying here, gently pressed into the world by the shape of time itself. Now, you might think this is all very lovely but very far away, a matter for eclipses and spaceships and equations, nothing that touches your actual life. And here is what is interesting. It touches your life constantly, more directly than almost any other piece of physics ever discovered, because you have, almost certainly, used space-time to find your way home. Think about the little blue dot on a map on your phone, the one that knows where you are with startling accuracy. That dot is found using a fleet of satellites circling the Earth at an altitude of about 20,000 kilometers. Each one carrying an extremely precise atomic clock, each one constantly broadcasting the time. Your phone listens to several of them at once, compares the tiny differences in when each signal arrives, and from those differences works out exactly where you must be standing. The whole system depends, utterly, on those clocks in the sky keeping near perfect time. And here is the thing that should make you smile. Those satellite clocks are affected by both of the strange effects we have walked through tonight. Because the satellites are moving fast, special relativity says their clocks should run slow, ticking behind the clocks on the ground by about 7/millionths of a second each day. But because they are high up, far from the Earth's mass, where space-time is less curved and time runs faster, general relativity says their clocks should run fast, gaining about 45 millionths of a second each day. Put the two together, and the satellite clocks gain a net of roughly 38 millionths of a second every single day compared to clocks on the ground. That sounds laughably tiny, but light and radio travel so fast that even a millionth of a second of clock error becomes a position error of hundreds of meters. If the engineers did not correct for both of Einstein's effects, your navigation would drift off by about 10 kilometers every day. Within minutes, it would be useless. The little blue dot would lose you completely. Every time you follow a map to a friend's house, you are quietly relying on the fact that time runs differently for clocks in the sky than for clocks in your hand, exactly as a patent clerk worked out 100 years ago. Space-time is not abstract. It is in your pocket. And then there is the most spectacular confirmation of all, the one that came only recently, within the lifetime of most people listening, and that I think is the most beautiful experiment ever performed by human beings. It begins, again, with a prediction Einstein made and then half-doubted. If mass curves spacetime, he reasoned in 1916, then a violent enough event, a sudden enough rearrangement of huge masses, should send ripples spreading out across the fabric itself. Waves of curvature, stretching and squeezing space and time as they pass, traveling outward at the speed of light. He called them gravitational waves, and then he worried they would be far too faint to ever detect. He was nearly right about that. They are unimaginably faint. Picture what such a wave would do as it washed over you. It would stretch space very slightly in one direction and squeeze it in the other, then reverse over and over as it passed. It would make you very briefly a tiny bit taller and thinner, then a tiny bit shorter and wider, then back again. But the effect is so small as to be almost beyond belief. A strong gravitational wave passing through the Earth changes distances by less than the width of a single atomic nucleus across the entire span of our planet. To measure that, you would need a ruler more sensitive than anything that had ever existed. So people built one. They built two of them, in fact, enormous L-shaped instruments called LIGO, one in the state of Louisiana and one in the state of Washington, far apart so they could check each other. Each one has two arms, each arm 4 kilometers long, with laser light running down them and bouncing off mirrors at the ends, much like the experiment of Michelson and Morley over a century before, but refined to an almost insane degree of precision. The whole design rests on the work of physicists who spent decades on it. People like Rainer Weiss, born in 1932, and Kip Thorne, born in 1940, and Ronald Drever and Barry Barish, who eventually held the project together and brought it to fruition. They were trying to measure a change in length thousands of times smaller than a proton. For years, many people thought it was impossible. They kept going anyway. And then, on the 14th of September, 2015, before the instrument was even officially running for its main search, a wave arrived, both detectors, 3,000 kilometers apart, picked up the same faint signal within milliseconds of each other. Exactly the delay you would expect for a ripple sweeping across the Earth at the speed of light. The signal lasted only about 0.2 of a second. It rose in pitch, a rising tone that scientists call a chirp, the unmistakable signature of two enormous objects spiraling together faster and faster before merging into one. And when they decoded it, they found they were listening to something that had happened over 1 billion years ago, on the far side of an unthinkable gulf of space. Two black holes, each around 30 times the mass of our sun, had spiraled into each other and collided, merging into a single larger black hole. In the final instant of that collision, an amount of mass equal to about 3 entire suns was converted, in a fraction of a second, into pure ripples in space-time. A burst of gravitational waves so powerful that, for that brief moment, it radiated more energy than all the stars in the entire visible universe combined, shining not as light, but as the trembling of the fabric itself. And those ripples spread outward across the universe, growing fainter and fainter, for more than 1 billion years. They passed countless stars. They crossed distances that have no meaning to a human mind. And at the precise moment, they finally reached the Earth. By then, a whisper of their former selves, there happened to be a machine here, built by curious and patient people, sensitive enough to feel them. The fabric of the universe rang like a struck bell 1 billion years ago, and we caught the last faint sound of it. Einstein had predicted those waves in 1916 and doubted we would ever hear them. We heard them just about 100 years later. 3 of the people who made it possible received the Nobel Prize in 2017 for it. And what they had truly done was reach out and touch the bending fabric itself. The very space-time we have spent all night learning to imagine and feel it move. There are two more places the fabric carries us tonight. Two final wonders. And then we will let everything go, soft and quiet. They are the two most extreme things space-time does anywhere in the universe. One is what happens when the curving becomes so steep that the fabric folds in on itself completely. And the other is what happens when you stand back far enough to see the entire fabric, all of it, doing something no one expected. Let us visit the first one gently, because despite its fearsome reputation, it is, in the end, just space-time being itself, only more so. We met black holes briefly, through Schwarzschild's battlefield calculation. Let me tell you what one actually is, in the language we have built. Remember that mass curves space-time, and that the more concentrated the mass, the steeper the curve. A planet makes a gentle valley, a star makes a deeper one. But if you could crush enough mass into a small enough space, the curve would grow steeper and steeper until, at a certain boundary, it became a cliff. At that boundary, space-time curves so sharply that every possible path, even the path of light itself, bends inevitably inward. There is no longer any direction that leads out, in the same way that, for you, there is no direction that leads into yesterday. Getting out of a black hole becomes as impossible as traveling into your own past, and for the very same reason. The fabric has tilted so far that the way out simply is not among the directions that exist anymore. That boundary is called the event horizon, and it is not a wall or a surface you could touch. It is a place defined entirely by the shape of space-time, a line beyond which all roads lead inward. And one of the strangest, most haunting things about it comes from the time bending we have studied all night. Imagine watching, from a safe distance, as something falls toward a black hole, a probe, a star, anything. As it approaches the horizon, where the curvature grows extreme, its time, as you see it, runs slower and slower. The object seems to fall more and more sluggishly, its motion stretching out, its light growing dimmer and redder until, at the very edge, it appears to freeze entirely, hanging there forever, fading toward black, but never quite seen to cross. From the outside, nothing ever finishes falling in. Time at the horizon, from our distant view, has slowed to a complete stop. And yet, for the object itself, nothing strange happens at the moment of crossing at all. It feels its own time running perfectly normally, sails across the invisible boundary without any local sign that anything has changed, and continues inward toward the deep mystery at the center. A place where our current understanding of space-time breaks down entirely, and where Einstein's equations stop being able to tell us anything we trust. Two utterly different stories. The frozen one we see and the smooth one the traveler lives, both true, just as with the twins, just as with the train and the lightning. The black hole takes everything we have learned about the flexibility of time and pushes it all the way to its limit. For most of the last century, black holes were purely a prediction, a thing the equations insisted must exist, but that no one had ever seen. And then, very recently, we saw one. A vast collaboration of astronomers linked radio telescopes from around the entire planet into a single instrument effectively the size of the Earth, and they pointed it at the heart of a distant galaxy called M87, about 55 million light-years away, where a monstrous black hole, some 6.5 billion times the mass of our Sun, sits at the center. In April of 2019, they released the result. It was an image, blurry and orange and unforgettable, of a bright ring of glowing gas wrapped around a circle of perfect darkness. the shadow of the black hole itself, the silhouette of a place from which no light returns. A few years later, in 2022, the same effort produced an image of the much closer giant at the center of our own galaxy, called Sagittarius A star, around 4 million times the mass of the Sun, sitting quietly at the middle of everything we call home. We have now seen, with our own instruments, the deepest curves the fabric can make, the places where space-time folds itself shut. They are not science fiction. They are out there, right now, anchoring galaxies, including ours, and we have photographed their shadows. And now, for the last great idea. Let us pull back as far as it is possible to pull back, past the black holes, past the galaxies, until we are looking at the whole universe at once, the entire fabric, every thread of it together. Because the fabric is doing something. It is not sitting still. It is stretching. For a long time, everyone assumed the universe was eternal and unchanging, a fixed and infinite arrangement of stars. Even Einstein assumed it. But in the 1920s, the evidence began to say otherwise. A Belgian priest and physicist named Georges Lemaitre, born in 1894, working from Einstein's own equations, found that they did not describe a static universe at all. They described one that should be either expanding or contracting, growing or shrinking, but never standing still. And at almost the same time, an American astronomer named Edwin Hubble, born in 1889, working at a great telescope in California, was measuring the light from distant galaxies and finding something remarkable. Nearly all of them were moving away from us. And the farther away a galaxy was, the faster it was receding. The whole universe, in every direction, was flying apart. Now, here is the part that matters for our story, the part that ties it all back to the fabric. The galaxies are not flying apart through space, like debris from an explosion racing outward into some pre-existing emptiness. That is the natural picture, and it is wrong. What is actually happening is that space itself, the fabric of space-time, is expanding, stretching, growing larger between the galaxies. The galaxies are more like raisins set into a ball of dough that is slowly rising in a warm kitchen. Each raisin sits more or less still in its own patch of dough. But as the dough swells, every raisin drifts away from every other raisin, and the ones farther apart separate faster, simply because there is more rising dough between them. There is no center to the swelling, no special raisin in the middle. Every raisin sees all the others receding and could believe itself the center, and none of them is. That is exactly what we see. We are not at the center of the expansion. There is no center. The fabric itself is growing, everywhere, all at once, carrying the galaxies along for the ride. And if the fabric is expanding now, then run the film backward, and everything was once closer together. Closer and closer, hotter and denser, until almost 14 billion years ago, the entire universe, all of space, was compressed into something unimaginably small and hot. That beginning is what we now call the Big Bang. Though the name makes it sound like an explosion in space, when really it was the beginning of space, the first stretching of the fabric itself. Lemaitre, the gentle priest, first imagined it, calling it the primeval atom. And we even have a faint echo of it, discovered by accident in 1965 by two researchers in New Jersey, Arno Penzias and Robert Wilson, who kept picking up a faint hum of microwaves in their antenna no matter where they pointed it. That hum turned out to be the afterglow of the early universe, the cooled-down light from when everything was young and hot, still drifting through the fabric after billions of years, falling on us from every direction at once. It is the oldest light there is, the universe's first dim glow, And a tiny fraction of the static you might once have seen on an untuned television was that ancient light, the warmth of creation arriving in your living room. There is one last gentle irony to leave you with. When Einstein first applied his equations to the whole universe, and they told him it could not stand still, he did not believe them. He added an extra term to force the universe to hold steady, because like everyone, he assumed it must be eternal. When Hubble's measurements later showed the universe really was expanding, Einstein removed the term and is said to have called it the greatest blunder of his life. And yet, decades after his death, astronomers discovered that the expansion of the universe is not slowing down, but speeding up, driven by something we do not understand and call, for now, dark energy. And the mathematics that best describes it looks remarkably like the very term Einstein threw away in embarrassment. His blunder may not have been a blunder at all. Even his mistakes, it seems, were reaching toward something true. The fabric is subtler than any single mind, even his. Before we let the night carry us under, I want to circle back, softly, to the strangest idea of all the ones we touched, because it is the one that lingers, and it is, I think, the most peaceful. It is the idea that there is no single universal now. We felt it with the train and the lightning, the way two people moving differently disagree about what is happening at this very moment far away. And we pictured it with a loaf of bread, the way each of us slices the same whole reality at our own slight angle. Take that seriously for a moment, here in the quiet. If there is no shared, cosmic present moment, if your now and the now of someone moving past you genuinely include different events, then the comfortable picture we all carry of a single bright line of present sweeping forward and leaving the past behind in darkness may not be how the universe is built at all. The past may not be gone. The future may not be waiting to be created. They may simply be other regions of the fabric, other parts of the loaf, every bit as real as the slice you happen to be standing in, just as the next room is still there, even when you are not looking at it. Physicists sometimes call this the block universe, the idea that all of space-time, past and present and future, exists together as one complete, four-dimensional whole, finished and entire, with no special moment that counts as the real now. In that picture, the flow of time, the powerful feeling we all have of being swept forward, is something that happens inside us, a feature of how we, as creatures made of memory, experience our own path through the fabric rather than something the fabric itself is doing. The universe does not flow. We move along our thread of it, and the movement feels like flowing. The way the countryside seems to stream past the window of a train that is, from its own point of view, simply sitting on its track. I will not tell you this picture is certainly correct, because honest people still argue about it, and the experience of time passing is so vivid that it resists every attempt to explain it away. But I find something deeply restful in even considering it. Because if it is true, then nothing that has ever happened is truly lost. Every good evening you have lived is still there, fixed in the fabric, as real as this one. Every person you have loved is still, somewhere along the loaf, laughing in a warm room. The morning you are sailing toward already exists, a little further along the same unbroken cloth, in no need of being hurried into being. There is nothing to chase and nothing to outrun. The whole of it simply is, and you are a thread woven through it. And tonight is one small, glowing stitch that will always, in the deepest sense, be exactly where it is. So whether or not the block universe is the final truth, let it soften something in you tonight. You do not have to hold the present moment tightly, as if it might slip away. In the fabric, this moment does not slip anywhere. It stays. It is part of the permanent shape of things. You are allowed to simply rest inside it, without guarding it, without grasping after the next one. The next one is already there, secure, waiting with infinite patience. So let us draw all of this gently to a close now, and let the ideas settle. Like sediment drifting down through still water until the glass goes clear again. Think of the long, quiet chain of people who built this understanding, one careful life after another. Galileo in Italy, noticing that smooth motion cannot be felt. Newton in England, giving us 2 centuries of solid ground. Maxwell in Scotland, discovering that light is a wave and asking the dangerous question of what it waves in. Michelson and Morley in a basement in Ohio, finding nothing and not knowing that their nothing would change everything. Lorentz and Fitzgerald, almost reaching the truth and stopping just short. Einstein in a patent office in Bern, trusting the universe over his own instincts and then spending 10 more years turning gravity into geometry. Minkowski in Cologne, seeing the single fabric where his old student had seen only a theory. Schwarzschild, calculating black holes from a battlefield, dying before he could know what he had found. Eddington, watching the clouds part over an island just long enough to photograph a bent ray of starlight. And in our own time, Weiss and Thorne and Barish and all the others, listening for a trembling of space-time fainter than an atom. And finally, after 100 years of waiting, hearing it. None of them rushed. None of them needed the answer tonight. They simply kept walking, slowly in the dark, toward something true. And now, bring it all the way back here, to this room. You are lying in a particular place, 3 numbers of space, and a particular moment. 1 number of time, a single point in the great 4-dimensional fabric, as real and as located as any event that ever happened. The bed beneath you is holding you up only because the earth has bent the space-time in this room. And your body, drifting forward through time the way everything must, is gently steered downward into the mattress. The very weight you feel, the soft pressure of the blanket, the way your head sinks into the pillow, all of it is the shape of time itself, cradling you. Gravity is not pulling you down tonight. Space-time is simply curving around you, and you are resting in the curve. And while you lie here, perfectly still in your small corner of space, you are not still at all. You are moving forward through time at nearly the full speed of the universe, carried into tomorrow whether you do anything or not, riding the one current you were never meant to steer. There is nothing you need to do to travel into the future. You are already doing it, effortlessly, right now, just by breathing, just by being. The fabric carries you, the way it carries the planets around the sun and the light across 1 billion years of darkness to a quiet machine in Louisiana. So let your shoulders go heavy. Let your jaw unclench. Let the strange and beautiful idea of one single fabric, bending softly under everything that exists, settle over you like one more gentle weight. The room is a slice of now, your own quiet cut through the loaf of all that is. The hour glowing on your clock is just the place along the loaf where you happen to be. And the morning is already there, a little further along the same unbroken fabric, waiting in no hurry at all for you to arrive. Rest now. The curvature is holding you. You do not have to do a thing.